All right, good morning, calculus class. As I had said, I will not there today. I will be here for tomorrow for when you actually have your test, but today you're just going to be taking, or will have already taken, a practice test. Now, please write with me. Go ahead and just write in the margins, or if your answer is on track and matches mine, awesome. I just need to make sure that you've got correct answers so that when you are going to study tonight, which you should be doing, you have correct work to go from. So, starting with number 1. We have this lovely limit, so we need to find the limit as x approaches 0 of this here rational function. Now, looking at this right away, if I just plug in 0, I'm going to end up with 0 over 0, which means that I got to do something to this first. And so if I'm looking at sort of seeing how can I change this, what I'm actually going to do is I'm going to pull out an x to the third power from everything. And so I'm going to have the limit as x goes to 0 of x to the third, and what's left is 8x squared minus 6 over x to the third, and what's left is 5 minus 2x squared. And now I'm going to cancel these, right? I have an x cubed and an x cubed, and so I have the limit as x approaches 0 now of 8x squared minus 6 over 5 minus 2x squared. Now, I can actually just go ahead and plug in 0, right? Because now if I plug in 0, what's going to happen is that this is going to go to 0, and this is also going to go to 0. And so what I'm going to be left with is negative 6 over 5. And that's my limit. On number 2, we need to figure out which of the following are true. So we're specifically looking at 1 from the left, the right, and then in total. And so from the left, we're approaching. We're getting closer and closer to that y value of 3. And so, yeah, I would say that this absolutely exists. From the right, let's take a look again. Approaching. We're still approaching that limit, or that y value of 3. And because that we are approaching 3 on both sides, it means that the full limit not only exists, but is 3. And so if we're talking about what's true, well, they all are. And so now on number 3, this isn't one quite like we've done. We need the x coordinate of the discontinuity. And so there's 2 potential places that this is going to be a problem, right? Think of everywhere that this is going to break. First one, 0. I can't have 0 here. And the second one is going to be negative 4, because if I let x be negative 4, then the denominator over here will go to 0. And so I need to test 2 points. X equals 0 and x equals negative 4. I'm simply looking to see, are we discontinuous at these values? And so the first thing I'm going to look at is going to be the limit. It's just going to be the limit. And so if I'm looking at the limit as x approaches 0, specifically I'll say from the right, I'm going to have 3 over x plus 2x over x plus 4. Now, this numerator is going to go to 0, so this entire right side of the fraction, that's going to 0. I don't have to worry about it. And so, apologies, this should be an x. All I'm looking at here is this first fraction. Now, when we think of 0 from the right, it means that we technically have positive values. And so there's positive values going in for x. And so that's really important because as we get closer and closer and closer to 0, so as this denominator gets smaller and smaller and smaller and smaller while staying positive, this is going to go to, I'll do it over here, positive infinity, right? As this x stays smaller, or gets smaller and smaller and smaller and smaller and smaller while staying positive, because we're from the right, we're going to positive infinity. The limit as x approaches 0 from the left, however, we're probably going to see a shift. I still have 3 over x plus 2x over x plus 4. Now again, this is going to 0. I don't really care about this second fraction. Everything that's important is happening right in here. And so we have, again, 3 over x, but this time, this denominator is getting closer and closer and closer and closer and closer to 0 with negative values, right? If we're to the left of 0, it's a really negative values. And so this is going to end up going to negative infinity. As soon as we see that this is going to positive infinity and negative infinity, we know for a fact that there's going to be an asymptote here, which is going to give us that infinite discontinuity. And so we know that there's one at x equals 0. I still need to check x equals 4, though. I do still need to check that. And so we're going to do the same thing. The limit as x approaches negative 4 from the right, 3 over x plus 2x over x plus 4. Now, if we're approaching negative 4 from the right, we're still having negative values, and so this is just going to a fraction, yes, but take a look at this denominator. This denominator is going to be what's important here. We are again approaching a tiny, 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 tiny denominator. As that's happening, this fraction is actually getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. So we are going to negative infinity because by default, I take that back. I'm ahead of myself. So apologies. Let's kind of zoom in on what's fully going on here, because really what we're looking at is 2x over x plus 4. Now, if I substitute in a negative, technically the bottom is going to be a negative, and the top is also going to be negative. And so, if we have a negative over negative, we have a positive. So it's going to be infinity. Again, let's take a look at from the left. Again, we're really just zooming into 2x over x plus 4 here. Again, I'm going to be having a negative over a negative. Again, I'm going to be given a positive. So the limit's going to be there and the limit's going to exist. However, the function value itself is going to be undefined. And so, again, what we're actually going to end up having is that infinite discontinuity at x equals 4. And so there's two of them, right? 0 and 4. Again, we had to make sure to see that it was a full discontinuity. And yes, it is. Moving on. So we have, suppose that h of t is equal to t squared plus 3t plus 2. We need to find the limit of h of t as t approaches 2. Now, there's nothing crazy going on. This is actually truly just looking at limit laws, and can we apply a limit algebraically? Remember that when we do that, we simply just substitute this value in for t. And so really, when we're looking at this limit, how we calculate it, h of t is simply going to be 2 squared plus 3 times 2 plus 2. It's going to be 4 plus 6 plus 2. And so the limit is 12. Questions like this, I'm hoping we're not deceived by how simple they truly are. It is really just as simple as plugging in that value. And now for 5, we've seen a lot of these. It's a limit with a piecewise. And so they'll find the limit of f of x as x approaches 1 from the right. Now, remember, if we have our number line, we have 1 right here. If we're approaching from the right, it means we're coming from this side, which means our values are actually greater than 1. So 1 from the right is greater than 1 is sort of a way that we can remember this. And so in terms of when we're greater than 1 per this piecewise, we have to use x plus 4. And so the limit as x approaches 1 from the right of f of x is something going to be 1 plus 4, which is 5. Again, the math here itself is pretty simple. What this question is really testing us on is, do we understand what this means here and how it interacts with this function? Now for 6, suppose we have this piecewise. We have bt if t is less than or equal to 3, and we have 4 if t is greater than or equal to 3. Find a value of b such that the function f of t is continuous for all of t. Now, we 100% have not done a question like this. However, we know what it means for this to be continuous, right? It means that at the value that is in question, which is going to be t equals 3, we need the limit to exist, which means that the left and the right hand need to be the same. we need the function to be defined, and we need both of those values to be the same number. And so truly what we're looking at here is we need to start by seeing what is the limit from the left, what is the limit from the right, what is the full limit going to be, and then making sure that the full function value has to match that. Okay, well, I'm going to start with the limit from the right. The reason for that is technically if I look from the left, right, left, it would be less than 3. I don't actually know what's going on. And so I have to match this to what information I do have. And so as we approach t, or t approaches 3 from the right of f of t, per this piecewise is going to be greater than 3, which means it's actually just 4. Now, what that means is that both the limit as we approach from the left and the function value actually just needs to be equal to 4. Right? Those are the only two things that need to happen. And so what that means pretty simply is that when we plug in 3 into b of t, we actually just have to equal 4. And so if I plug 3 in for t, what that means is I'm going to have 3b equals 4. And so I just divide both sides by 3 to learn that b has to be 4/3. In order for this to be continuous everywhere, right, in order for the left-hand limit to also equal 4 and the function value itself to equal 4, b needs to be 4/3. And so on a question like this, we simply find the limit that we can find based off of the piecewise, and then we know that whatever that answer is, the rest of the values just have to match that. And so we force it to. 3b equals 4, divide by 3. All right, for number 7, we are just looking to test continuity. And so there are 2 points that we need to test per this piecewise. We have that x equals -1 and +1. Now, I don't need to write the positive, however, just being clear in my distinction. So let's start with the limits. The limit as x approaches -1 from the right, I'm actually greater than -1, which means that I should be using x squared plus 1. And so that's going to be equal to -1 squared plus 1, which is going to give me 1 plus 1, which is 2. Wonderful. Now the limit as x approaches -1 from the left, if I'm less than -1, I need to use 2x minus 1. So I'm going to have 2 times -1 minus 1. It's going to be -2 minus 1, which is going to give us -3. These are not the same, which means that the limit as x approaches -1 does not exist, which means right away this is a discontinuity. Right away. And so f is not continuous everywhere. We know for a fact that that's not true. Question now is, okay, what's happening at +1? So let's take a look. If I am taking the limit as x approaches 1 from the right, I am greater than 1, and so I should be using this bottom function here. So I'm going to have 1 plus 1, simple enough, 2. Let's check from the left. X approaches 1 from the left. That's going to be 1 squared plus 1. Well, 1 squared is 1 plus 1, that's 2. Okay, well that's looking good. So that means that the limit as x approaches 1 not only exists, but actually is 2. For continuity, the only thing we need to check now is the actual function value. And so f of 1, well, per this, we should use the middle, right? Because that's the inequality that has equal to. That's going to be 1 squared plus 1, which again is going to be 2, which means at +1, we are, right? All of this information tells us that we are continuous at x equals 1. And so, given what we know, this function is continuous everywhere except at x equals -1. And so that means that b is not it, c is not it, and D is not it, and E is not it, and that C is correct. F of is continuous everywhere except x equals -1, because at -1, the limit doesn't exist. Moving on. The figure shows the graph of the function f with the domain 0 is less than or equal to x, which is less than or equal to 4, which those statements are true. We're looking at this small graph right here. And so we're simply looking at 2. Okay, let's take a look at the limit. Now, 2, right away, I can see, quite frankly, that this is a jump discontinuity. When we have a jump, I know already that the full limit is not going to exist. And so I know this is going to be true and this is going to be true, right? Because we're approaching actual y values, but this third one's not true. So if we're talking about what's true, just the first two. But because of the jump discontinuity, those two are going to be different values, which means that the full limit will not exist. And so for which of the following does the limit of as x approaches 4 of f of x exist? So we're simply looking for where are we approaching the same y value on either side of 4? Well, if we take a look, yes, we can see that there's a removable discontinuity, but remember that a removable discontinuity simply means that the function value is not going to be the actual limit, but this limit is going to exist. And so for 1, we're good. For 2, again, we're looking at a removable discontinuity. We're getting closer and closer and closer to the same y value, which means that the limit exists there. But over here on 3, again, just like the problem before, we have this jump discontinuity, and at this point, we should know that anytime we see a jump, we know that the limit will not exist. So it exists for 1 and 2, but not for 3. All right. Now, for number 10, we are looking to find the limit as x approaches infinity of this wonderful rational function. So what this question is actually asking us is, can we figure out what the most dominant function is? And so looking at this, they're actually all just polynomials. And so what I'm essentially going to have to do is just fully write this out and check my leading terms. And so I'm going to just do out all of this polynomial multiplication. Simple as that. I'm going to have 8x cubed, right? Draw my annotations so I make sure I have everything. Minus 2x squared. Oh, this should be cubed. That's really important. Minus 16x plus 4. And that's all over. Now I have to deal with this square first. And so I'm going to have x squared plus 2x plus 1. That's still times 3x minus 1. So again, I just got to multiply those through. And so up top, I'm actually just going to ignore everything that's not the leading term. I know that the top value is 8x cubed. That's all I need to know because of this infinite limit. And so underneath, I'm going to have 3x cubed plus 6x plus 3x minus x squared minus 2x minus 1. Again, I'm ignoring everything that's not a leading term. I don't need to know about that. And so really, when I'm looking at this, I'm looking at 8x cubed over 3x cubed. As this goes to infinity, these are going to grow, or these x's are going to grow at the same rate. And so what I'm really looking at is that the limit is going to be 8 over 3. Remember that with infinite limits, we simply look at the coefficients. All right. And so now, 11, we're actually doing the same thing, only there's just way less math, right? I don't have to multiply anything out. I'm simply looking for what's the most dominant function. Well, take a look. Between polynomials, it's whatever has the higher power, which means that our denominator is going to be increasing at a substantially greater rate than our numerator. When that happens, when our more dominant function is in our denominator and going to infinity, we're going to 0. So this infinite limit is just 0. If it was in the numerator, we would be going to infinity. It's not, so we're going to 0. All right, number 12. This is limit laws. Remember that with limit laws, all it simply is telling us is just plug in the limits, right? We simply take these limits and we plug them in. And so if I'm evaluating the limit as x is approaching 6 of all of this, I'm actually just plugging in these values. And so what I'm actually going to have is 7 times the cubed root of 27, right? Because that's that f of x value, minus 6 times negative 2, which is g of x, over 7 plus, again, negative 2, because that's g of x. And so what I'm going to have is 7 times the cubed root of 27 is 3, and then negative 6 times negative 2 is really plus 12. That's all over. Well, 7 plus a negative 2, it's really 7 minus 2, so 5. So I'm going to have 21 plus 12 over 5, which is going to give me 33 over 5. That's my limit. Again, simply just plugging in those values. Anywhere I see an f of x, 27. Anytime I see g of x, -2. So 13 is simply just asking us about a limit. And so if the full limit as x approaches a of f of x is equal to L, which of the following expressions must be true? Now remember, if this is true, that means that the left hand and the right hand, so x approaches a from the right and x approaches a from the left, both of them have to be equal to L as well. If either of these doesn't happen, this can't happen. And so let's see, we're probably looking for something that looks like this. F is continuous at x equals a. We don't know that. We have no idea what the actual function is doing at x equals a. We don't have enough for this. F of a does not exist. Again, we don't know the actual function, so I can't make any comments on this. And C, again, I don't know what the function is, so again, I can't comment. D, however, as x approaches a from the right, that equals L. Well, yeah, as we'd said, it has to. Otherwise, this can't be true, and so it is D. Now, 14, again, we are simply looking to see, do we know what the most dominant functions are? And so again, we're just looking at leading terms. I have 6n squared over 3n squared plus 10,000n. Now, as big as this coefficient is, I don't care about it. The reason for that, it's the least dominant function in that entire fraction. And so I'm really looking at 6n squared over 3n squared. And as that goes to infinity, again, we're just looking at our coefficients. We're going to have 6 over 3, which is 2. 15, if the function f is continuous for all real numbers for this lovely fraction, when x is not equal to 3, then f of -3 is equal to... So, again, this is one of those questions that we haven't really seen something quite like it. And so, essentially what we have to do is we just have to find the limit of this. We know that the limit has to exist, and for this to be continuous, the function value needs to equal the limit. And so f of -3 has to be whatever the limit is as x approaches 3. And so the limit as x approaches -3 of x squared minus 9 over x plus 3. Well, right away, that's going to go to 0 over 0, right? -3 squared is 9 minus 9, 0. -3 plus 3, 0. Which means that there has to be something else that we can do first. Now, if you take a look at the top is something really, really special. It's the difference of squares. And so, I know as much as we love to do it, we have to factor. And so really what I'm going to have is x plus 3 times x minus 3. Ooh, minus 3, there it is, right? Because difference of squares, it's really the square root of both with a plus and then with a minus over x plus 3. And now if you look, I can actually just cancel out this term. And so the limit itself is going to be just looking at x minus 3. Well, now I can plug that -3 in. And so -3 minus 3 is going to be -6, which means that f of -3 has to equal -6 in order to maintain continuity. All right, now, for 16, now, important piece here. These are 1 point each. This question is worth 8 points. And so, we're simply looking for, what are the limits? All right, let's take a look. X approaches -1, that's a full limit. Here's -1. From the left, we're coming into what looks like 1. From the right, however, we are up here. This is a jump. And so, right away, I can see these two limits aren't going to match. DNE. Simple as that. Let's take a look at 6. From the right, as we approach 6 from the right, we are hitting the y-axis, or sorry, the x-axis, so that means it's going to be 0. And so, ooh, apologies. I should be looking at -6, not +6. And so let's move down to -6. -6 from the right, approaching. We're looking at -2 right here. And so that's going to be -2. And if we now are being asked for the full limit, well, let's think about that, right? We said that this was -2. Coming from the left, we're also hitting -2, which means that this is in fact -2. Yes, we have a removable discontinuity, but remember the removable discontinuity doesn't have any issues with the limit actually existing, and in most cases, or all cases, it should exist. And so now we're looking at -4 from the right. Well, -4 from the right, we have a vertical asymptote. And as we approach -4 from the right, we're going up, 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 up. So we are going towards positive infinity. If we take a look at now, x approaches 4 of f of x plus 4, well, remember, this is actually just a limit law question. Don't be confused that this and even the next one we're going to look at is truly just a limit law question. And so let's go find the limit as x approaches 4 of f of x. Well, as we approach 4, here we are. Again, yes, removable discontinuity, but as we approach from either side here, we're approaching this 5 value. And so it's really 5 plus 4, which is 9. On this next one, I have 3 times f of x as x approaches 2 from the right. And so here's 2. We're going to approach from the right. Now we have a horizontal line at 5, so pretty simply this is just going to be 5. And so we're going to have 3 times 5, which is going to be 15. Again, for the limit laws, we're just plugging in those limits and then doing whatever extra calculations in arithmetic we have to afterwards. Now the limit as x approaches 4, let's take a look. Now, we actually have already named what this is, right? For this limit law, we had to find that this was 5, and so we should already know that's 5. Only one that's left is x approaches 0. Again, we have just this horizontal line at x equals 0, which means that there's going to be 0 problem with this existing, and that this is also going to be 5. Now, I'm hoping that these are fairly straightforward. We're truly just looking at the graph and seeing what our line is doing. Remember that removable discontinuities don't bother the limits. It's only going to be asymptotes and jumps that will bother limits. All right. Now, 17. I need to be super clear. Take a look at this. This is 5 points. This one question is 5 points. So let f be a function defined by f of x, and we have this lovely piece here. Show that f is continuous at x equals 0 using the definition of continuous. So we know a few things. The limit needs to exist. The function has to be defined, and those values need to be the same. So, as always, let's start with the limit. The limit as x approaches 0 from the right, again, that's going to be greater than 0. It means that we should be using this piece here, is equal to e to the -4 times 0. Now, -4 times 0 is 0. Anything raised to the 0 is 1. Okay, let's take a look at the limit as x approaches 0 from the left. That's going to be less than 0. Per this function, we're going to be using 1 minus 2 times the sine of 0. Now, if you don't remember the sine of 0 off your head, use your calculator. However, I hope that we do, because the sine of 0 is just 0. 0 times 2 is 0. So we're really looking at 1 minus 0, which is 1. All right. These two things together tell us something important. The limit exists, and specifically limit as x approaches 0 is equal to 1, right? Both of these are equal to 1. Full limit is 1. And so now the only thing we have left to do is check out the actual function value at 0. Well, for the function value at 0, we should use that second function. So again, I'm going to have 1 minus 2 times the sine of 0. But we just did that. And so we know that that's going to give us 1. And so I know that the limit exists, the function is defined, and these two are the same, which means that f of x is continuous at x equals 0. Wonderful. Now, last question. We're looking at velocity and acceleration. Determine if the particle is speeding up or slowing down at t equals 5. Now, when we see speeding up or slowing down, we're actually looking to see, is our acceleration positive or is our acceleration negative? And so I actually don't care about the velocity function at all for this question. I'm simply looking at acceleration and plugging in 5. And so I have a of 5, which is going to be 6 times 5 plus 5, which is 30 plus 5, 35. This is positive, right? This is a positive 35, which means that we are speeding up quite quickly, in fact. If our acceleration is 35, we're going pretty fast. And so now we need to find the average acceleration of the particle over the interval 0, 2. Now, this average acceleration, we've seen questions like it. I don't want us getting tripped up. This is literally just slope. It's literally find the slope between 0 and 2 using this essentially slope-intercept function. And so I'm going to start by finding the a of 0. That's going to be 6 times 0 plus 5. Well, that's going to be 5, okay? Now I need the a of 2. It's going to be 6 times 2 plus 5. It's going to be 17. So when I'm looking for this, again, it's just slope. And so I'm going to have 17 minus 5 over 0. Oh, apologies. Over 2 minus 0. 17 minus 5 is 12. Over 2 minus 0, well, that's 2. Which means that the average acceleration is 6. We're not given. We can assume, I guess, units per second squared. But for now, 6. Again, just slope. So, you now have answers to all of these questions. I will be putting this video up on Google Classroom, right? Because this is just going to essentially be a YouTube video. My expectation for you tonight is that you are at least watching this video, studying from this packet, whatever you need to do to make sure that you're in good shape tomorrow. Remember, I am still absolutely holding up that deal that if we average as a class 50 or greater on this test, we 100% will have a party next week. So I look forward to seeing you tomorrow for actually taking your test. Should you have any questions after we've gone through this, feel free to email me. But again, I look forward to seeing you tomorrow.